So, we will continue our discussion. So, for multi-electron atom, what we have seen so far, for closed subshell L and S are 0, that is important conclusion. And then another things we have seen this equivalent electron and non-equivalent electron. Non-equivalent electron, just using the vector model one can find resultant L, capital L means resultant angular momentum, orbital angular momentum, resultant spin angular momentum, capital S, and then this total angular momentum, that is J. Okay. Just using vector model one can whatever the value of L and S and J will get, all are allowed. Okay. It does not violate the Pauli exclusion principle because they are non-equivalent, either N or L are different already. So, we will not bother about ML and MS, they can be same, they can be different. Okay. But when it is their equivalent electron, means N and L are same, then using vector model we will get resultant capital L, resultant capital S, but we have to find the combination for each L, each S may not be allowed. We have to see whether this any combination is violating the Pauli exclusion principle. So, that is what we are doing, and this for S2 I have shown you how to calculate. Then P2, these are 2 electrons. So, but in P we can put 6 electron, maximum 6 electron. Okay. Now, for P1 I have calculated, P2 I have calculated. Now, for P3 if I put one more electron, so then you have to calculate this you have to calculate. So, you have to think. So, just I can start from here. So, P2, so for that resultant L, capital L and resultant capital S I got. Okay. So, that is there. So, that is the from 2 I got the resultant vectors for capital L, capital S and say capital J also one can get. Okay. So, let us check for L only first. So, L1 and L2, so vector sum I got the L resultant L. Now, this resultant L is there, capital L is there. Now, I put one more electron, so L3 then. Okay. So, now forget L1, L2. So, I have this capital L. Now, with that resultant one I will do the vector sum of the third one. Okay, L3. So, if I start from resultant L and S for P2, and then only I have to add one more electron where L3 and S3 is 1.5. So, basically where to write. So, here let me write. So, additional one I am putting L3, L1, L2, then I will put L3, then say here L3 equal to 1, P, S3 equal to half. Okay. S3 equal to half. Now, from these two already I got this one. Now, if I take, let us take just this value and add the third one. So, for L equal to 2, okay. Now, I will add this L3. So, what I will get? Just vector sum. So, I will get 1 and this is 2, I will get 3, I will get, because summation is this resultant whatever L, and then plus L3. So, from this value to L minus L3, okay. This vector sum is same way. So, if I, so these two L plus L3 minus 1, L plus L3 minus 2, L plus L3 minus 4, etc., up to L minus L3. Okay. So, for L, S and J, for everything these are same way we do vector sum. So, then I will get resultant one. Resultant L I will get basically, so this is for 2 electron and this is 1. So, what I will get for L equal to 2, here I will get L equal to 3, 2, 1, because this 2 minus 1, 1. So, 3, 2, 1 I will get. Okay. And then for L equal to 1, here if I take L equal to 1 and then corresponding if I take the L3 add. So, for that I will get basically for L equal to 1. So, 1 1. So, I will get 2 1 0, right. Resultant L I will get 2 1 0. Now, L equal to this is 0 and this I have to add with L equal to L3 equal to 1. So, I will get basically 1, right. I will get basically 1. I will get basically 1. Okay. So, basically resultant one now we are getting, this the for third electron L values are these are allowed. So, basically L value 3 2 1 2 1 0 1. So, ultimately I can write L value we are getting 3 2 1 0, this 4 L value we are getting, right. Now, we see that L3, L equal to 3, I have 3 electron. So, now L equal to 3 means capital ML, it will be plus 3 to minus 3, plus 3 plus 2 plus 1 0 so I will get 7 value, right. So, ML, capital ML is plus 3 means what does it mean? ML1, ML2 and ML3 all has to be plus 1, right, because the summation capital M L. So, for L equal to 3 capital, so for L equal to 3 ML, one value of ML maximum value, this will be plus 3 and this will come basically sum over ML, individual ML, ML1, ML2, ML3. So, only it will come this for plus 1, plus 1, plus 1 and plus 1, right. There is the other option. So, that means ML value for 3 electrons are same, NL of course the same, ML also same. Now, S has to be different, sorry, MS has to be different. So, MS value only 2 choice are there, MS equal to, I mean this individual MS, individual MS. So, now total MS I have to find out. So, that will come from the sum over MS, small MS. So, small MS it has only 2 choice, plus half and minus half. Okay. Now, for 3 electron I have to give MS value. So, one I can give plus half, one I can give plus half, another I can give minus half. Okay. So, they are different, fine, but what about the third one? Either I have to give plus half or minus half. I cannot give that one because then 2 of them will be identical. So, all MS has to be different, okay, and that is not possible. Third one I cannot put. Okay. If I put plus half, then these two will be same. If I put minus half, then these two will be same. Okay. and it will violate the Pauli exclusion principle. So, L equal to 3, that is not allowed, okay. And then you can show that L equal to 2, 1, 0, these 3 values are allowed, okay. These 3 values are allowed, and corresponding MS one has to think. So, now L equal to 2, capital L equal to 2, okay. Capital L equal to 2 means capital ML, that ML value, ML capital, these are, if I put this 2 now, these are 2 for L equal to 2, ML maximum ML value 2. So, 3 electrons ML 1. So, what can be the combination? +1 and another one is 0, ML value is 0, right. Because small ML value, these are 3 +1, 0 -1, these are 3 allowed value. So, I can take this combination +1 and 0. So, then total ML I am getting 2, fine. Then MS, I have to put 3 MS, it is fine. You see, these two are same, ML value same. So, I will put plus up and this is minus up, fine. Now, this ML value 0, it is different from the other one. So, then I can put either plus up or minus up. So, generally whatever you wish you can put. So, generally we put plus value plus up, okay. So, when L equal to 2, we are getting MS is half. This MS we are getting, capital MS we are getting half, okay. So, that means S has to be half, S has to be half. So, in this case for L equal to 2, S will be half. So, what we are getting for P3, what is P3 I have not written. So, P3 electron, okay. So, one value we got L equal to 2 and S equal to half. L equal to 2 means D, L equal to 2 I will write D, term is D, and S half means this is 2, okay. And J you can find out, that we will see later on. Now, L equal to 1, if I take L equal to 1, if I take L equal to 1, okay, then ML, maximum ML value will be 1, okay. So, sum over ML is how I can get this one, I can get plus 1 minus 1. If I put minus 1, if I put minus 1 here, okay, then ML value will be plus 1. Other combination may be possible. Generally here we try to take the this how many same value we can take here, okay. So, dependent value does not matter, because it will obviously it will not violate the Pauli exclusion principle, but we should check taking the maximum number of same value of ML and MS, okay. So, here this maximum ML same value +1, then obviously third one I have to put minus 1, I have to put minus 1, okay. So, then it will be 1, and then MS equal to, so for this MS plus up and this minus up I have to take, there is no way, and this is different from the, this minus 1 ML value is different from the other. So, this again I can put this plus up or minus up. So, we can take plus up. So, next I am getting, so MS equal to half, that means S has to be half, S has to be half, okay. Yes. So, next another term I am getting L equal to 1, that means that will be yeah, for this term another term will be P and S is half, so it is 2, okay. And then ML equal to, then L equal to 0, then L equal to 0, Okay. So, ml will be 0, ml will be 0, ml will be 0. So, how we can get 0? How we can get 0? We can take plus 1, minus 1, then it is 0, and this other one there is no option, one has to take. So, plus 1 and another I have to take minus 1. Okay. Then it is 0, then third one I have to assign this 0, ml value 0. So, then it will ml 0. So, S here you see these 3 are different, plus 1, minus 1 and 0, ml value are different. So, I can take S value same, okay, because I have to try to take summation sum over whatever ml or ms, generally we try to take the maximum value, one should take the maximum value. So, ms for all I can take plus value, because as I told you this always we should try to take the same value of ml and ms as many as possible. Okay. If they are different, there is no problem, it will not violate. If they are same, so then that is the critical point one has to analyze. So, ms value I can take same, then ml value will be here it is becoming different. Okay. So, here it is ms value 3 by 2. So, s value has to be 3 by 2. Okay. Maximum ms value is 3 by 2. So, this s value has to be 3 by 2. So, for L equal to 0, so L equal to 0, another term we are getting s, L equal to 0 s, and this 3 by 2 means it is 4, okay, 4s. So, this way here we are getting this 3 term from p equal to 3. So, now here let me so here, so what will be the j value? Here L equal to 2 and s equal to half, L equal to 2 and s equal to half. Okay. So, s equal to half, then obviously it will be 3 by 2 and 5 by 2, j will be 3 by 2, 5 by 2. So, j will be 3 by 2 and 5 by 2. You see 2 again multiplicity 2, it is 2, and p it is 1 and s half. So, it will be half and 3 by 2, okay. And this s is 0 and s means L is 0 and s is 3 by 2, that means this j will be 3 by 2, okay. As I told, in case of s, this multiplicity number of term it does not follow the multiplicity, okay. Otherwise, for other cases this number, this multiplicity is this number of j value, okay. So, this way one can find out. So, up to now P3 I showed you, P4, P5, P6, okay, one can find out. So, here I will tell some rule, from the observation. Let me so, yeah. So, one observation, one rule is that here I mentioned you, for closed subcell or closed cell, L and S are 0, resultant L and S are 0, and then for non equivalent electron all LS are allowed and corresponding spectroscopic term one can find out, that is not the difficulties, but difficulty is for the equivalent electron. N and L are same, okay. Those are called equivalent electron. For equivalent electron, what are the state? What are the state one has to or spectroscopic term one has to find out, and how to find out? I told you one way. There are different way also people use. So, you can try which one is better for you, but I told you just one way. So, that can be applied for here I showed S electron, then P electron, P equivalent electron, then there are D equivalent electron, etc., F equivalent electron. So, here one thing I can tell you that this here say P2. So, what I got? I got basically for P1, what are the state I got? This P1, this is the state P1, I got 2 P half and 3 by 2, and then I got for P2, this is for P2. So, for P2 electron, equivalent electron. So, here these are the states, What are the states? 1 is 0, then 3 P 0 1 2, and then D 1 D 2. So, these are the spectroscopic term, means these are the energy levels, these are the spectroscopic, these are the energy levels for the system. Yes. So, and then we found P3 what you got? This I got 4 S 3 by 2, then 2 P half 3 by 2, and then I got D it's a 2, and this 3 by 2 and 5 by 2. Okay. Now, you will get basically for you have to find out for P4, P5, P6. Okay. So, without further calculation I can find out. So, rule is that, so this subcell it contains maximum 2, it contains maximum 2l plus 1 number of electrons, right, 2l plus 1 number of electrons. Okay. So, for any either P or any spectroscopic any for either s orbitals or p orbitals, d orbitals, f orbitals. So, for any orbitals, so if you calculate for so say q number of I think let me write just R one general R, it can be S no, let me write I think these are L value. So, let me write L, okay. Let me write this L, but it may be confusing. So, what I should, okay, anyway. So, in this case it is P. So, let me write P. So, P can have maximum 2l plus 1. So, P can take in general. So, P equal to 1 means 1, it can take 3 how many electrons? 6 electrons. Okay. If here P I have written, if it is P in general, Okay, if it is D, if it is S, so one can write this way. Okay, so for the spectroscopic term, whatever I got, it's for PR and P, this maximum number of electrons it can have minus R. Okay, the spectroscopic term will be okay. Let me write just end. So PR. So now in case of P1, this 1, and in this case it is 1 and this is 6, 5. So whatever spectroscopic term for P1, the same spectroscopic term will be for P5. So these are the spectroscopic term for P5 also. Okay. And then P2 R2, so this will be 6 minus 2, 4. So this spectroscopic term is for P4 also, right. Okay. So you know P1, P2, P3, P4, P5 and then P6. P6 obviously for closed subcell it is L equal to 0 and S equal to 0. That means its term will be S L equal to 0, this is L, S equal to 0, this is 1, okay, and J will be 0. So this. Okay. Similarly for D, one can calculate, I will not calculate. So D is 1, D1, D2, D3, D4, D5, right. So if you calculate up to D5, then D6, D7, D8, D9, D10, D10 obviously it is the same 1 S0, L equal to 0, S equal to 0. D9 it will be same as D1, D8 it will be same as D2, D7 it will be same as D3, D6 it will be same as D4, right, and then D5. Okay. So this is your homework, you can try to calculate the way I have calculated, or there are some other method also people try to use. So this now how to find out the spectroscopic term for multi-electron atom, that I try to calculate, and this very important. This each spectroscopic term is telling basically the state of this atom, state of the atom, energy of the atom, in which state it is. Okay. Now here for non-equivalent electron there is no problem, for equivalent electron one has to be careful to calculate, that is also we are able to calculate. Now here whatever I have data, now if I ask you, or if we try to find out that here is for P1 electron for ground configuration of the, so it is P1 electron, it may be atom say lithium, alkali atom, lithium atom, okay, lithium atom, potassium atom, sodium atom, okay. So because 1s2, 2s2, 2p1, okay, right, that will be for no, sorry, it is not lithium, not alkali atom, because that is S electron. For alkali atom that is S electron. So S data I do not have here. So but I have calculated. So, for p electron this is basically 1s2 2s2 2p1. So, that is boron, right, it is boron, and this for other you have to see this in that column of the periodic table. So, whatever the other in that column. So, basically this column formed with this outer electron, So, all P1 that will be in one column, P2 electron this another column, etc. And yes, and there is no last column is for inert gas, and for inert gas this the outermost electron, outermost subshell is closed. Okay. So, all subshell are closed. So, that way basically so periodic table is arranged in different row depending on the outermost electron, whether it is S1 or it is P1 or it is others. Okay. So, here what I am trying to find out, electronic configuration, it is whatever this way, this is the minimum energy configuration. For any atom you can give minimum energy configuration, and for a particular atom. Okay. So, outer shell is P, and in that P if it is 1 electron, okay, before that it is closed, subshell are closed. So, there is the contribution of L and S because they are 0. Now, only contribution from P1, then put one more electron, then you will get the next atom, that is P2, P3, P4, P5, P6, etc. right. So, but when this for this atom, okay, it will have two states, P half and P3 by 2. Okay. Now, again two states. Now, among these two states, which one will be the ground state, which one will be the minimum energy state, or both are having the minimum energy? It cannot be, because we know this energy depends on J value, Nj we have seen. So, lowest J value is the lowest J value will have the lower energy state, okay, and higher J value will have the higher energy. So, obviously this one means 2p half, this one will be the ground state, this one will be the ground state, okay, and 2p 3 by 2, its energy is higher than the 2p half. So, one can, if someone asks which one is the ground state, so out of these two we can find out. Okay. So, similarly we can find out here there are, say, for P2, okay, there are many states. So, how to find out the ground state? Okay. So, here S is same, L is same. So, depending on J we could find out, and here how to find out? Here different terms are there. Now, it is important rule to find out the ground state, and for equivalent electron. Okay. So, this is Hund's rule, Hund's rule. To find out the ground state, okay, of multi-electron system, and it's and for equivalent electron configuration, these are for equivalent electron configuration. What is the ground state that we can find out taking the help of Hund's rule? What is Hund's rule? Hund's rule is that to get the lowest energy state, ground state, first we have to, which this term is having L, S, right, and J, L, S and J, right. So, out of them how to find out? Out of them how to find out? So, Hund's rule is telling, first we have to maximize S, okay, which will have the lower energy. Whatever the terms are available, so maximize S. So, here whatever terms are available, what is the maximum S? This one is having maximum S, S equal to 1 in this case. So, now I select this one. Okay. Then next step, after selecting this S, then I should maximize L. I should maximize L. Okay. So, now here you see I have only one L. If another term would be there, so 3p and here also 3d kind of things, then maximize S means out of them, so 3 would be the maximum, then I have to maximize L. So, then whether p I will consider or d I will consider. If it is 3d, okay, 3d2, so then I will consider d. Okay. Since here I do not have any choice, only one term, only one L value, so I will choose, I have to choose this. Okay. So, maximize S first, then maximize L. So, this is the term, and then out of these 3, P0, P1 and P2, which one we should consider. Okay. So, then this Hund's rule is telling that that basically this for equivalent electron, I told for it is valid for equivalent electron configuration. So, lower J will have the lower energy. Okay. When we will get, so basically it is telling we will get lower energy. Okay. Lowest J value will give the lower energy for less than half filled cell or subcell, for less than half filled subcell. Okay. And higher J value will give the lower energy for higher than half filled cell subcell. Okay. What does it mean? So, I will get lower energy J value lowest J value will give the lowest energy state. So, when it is so which J value, this L minus S, that will be the lowest energy state for less than, when is for less half filled cell, less half filled cell. Okay. When cell or subcell is cell or half filled. Less than half filled, when cell is less than half filled. Okay. Less than half filled means it is less than P3, so up to less than for P1, P2. So, lower J value L minus S, and for higher than J value, higher than half filled, so that is for J equal to L plus S. Okay. So, that means for P2 this one will be the S is maximized, and then L there is no choice, and out of them lower, this is the J value, lowest value. So, this will be the ground state, for P2, but for P4 it is higher than the half filled, because P3 it is higher than the half filled. So, for that L plus S means maximum L, maximum J. So, for that one, so this will be the, I think I will use, so this will be the, so P3 P2, that will be the ground state for P4. Okay. So, for P4 this you have to find out which atom it is depending on this n value. Okay. So, this way one has to find out. Okay. So, how to find out the ground state? Okay. It is whether it is less than half filled or higher than half filled, depending on that this ground state will be different. Okay. So, that is valid for all subcell, whether it is D or this is F. Okay. So, I think this so how to find out the ground state of an multi-electron atom. Okay. So, this is the way one has to find out for any atom, okay, having many electrons. You know this, say chromium is 24 number of electrons, copper is 29 number of electrons. Okay. For all of atoms, one has to find out first. You take the electronic configuration of that atom, 1s2, 2s2, 2p6, etc., etc. Okay. Then closed subcell LS value are 0, so neglect it. Then only unfilled subcell. So, unfilled subcell will be S1, P1, P2, P3, P4, P5, P6 again closed, D1, D2, D3, D4, D5, etc. Okay, F1, F2. Okay. So, for that you have to find out spectroscopic term. For equivalent electron, how to calculate. For non-equivalent electron, that is all terms are allowed. Now, you will get many terms for this electronic configuration, for a particular electronic configuration, and out of them you have to find out ground state, which one is ground state. So, you have to take help of Hund's rule. Okay, is telling first maximize L, maximize S. So, you have to find out what is the maximize S. So, in this case this is the maximum P3 maximum S. Okay. Then I will select this term. So, there is no 4 other. So, L is same. Now, here is 3/2, there is no other choice. So, it is interesting. So, here we talk about the less than half filled and higher than half filled. Okay. So, what about this half filled? Okay. Interestingly, for half filled only one term. Okay. So, you do not need to do anything, and that has happened. Okay. Maximize S and then L, then that is having only one term. Okay. So, this way one has to find out the. So, if I can find out the spectroscopic term for an atom, then everything is done. If I know the spectroscopy, as I mentioned earlier, for single electron atom, if I know the spectroscopic term, then I can do everything. Spectroscopic study, I can do everything, right. I can what I want to do, I want to study the spectral lines. So, if I know the spectroscopic term, so I can find out the corresponding transition and I get the spectral lines. If I apply magnetic field, then I can find out the Zeeman effect. If I apply Zeeman effect, right. So, I can calculate the basically I have to this energy I have to calculate. EV equal to mu j dot B, right. So, mu j is what is the mu j? Mu j is Gj j, mu j is will be Gj mj Gj mj mu b, right. Okay. Yes. So, Gj, you know, 1 plus j square plus L square minus a square divided by no 1 plus j square plus a square minus L square divided by 2 js. Okay. So, Gj one can find out. So, Mj you know, everything you know if you know the spectroscopic term. So, you can find out the effect of magnetic field. Similarly, you can find out the effect of electric field on that atom. So, to find out the effect of electric field, magnetic field or light or the transition transition of electrons in the atom for which we get the spectral lines. Okay. So, everything you can find out if you know the spectroscopic term, and that is what we have done for multi-electron system. So, here we have seen, we have considered some rules, Pauli exclusion principle, Hund's rule, etc., Auf-bau principle, this etc. So, these all are valid. These are simple rules, but everything one can find out from quantum mechanical treatment. If you use quantum mechanics, then all things can be explained, but there are difficulties. For single electron it is easy, for multi electron is difficult, but one can qualitatively one can explain them, quantitatively rather it is difficult. So, I think I will stop here. Next I will try to use quantum mechanics